بەنای خۆی گەورە میرەبان سلااو قوتابیانی عزیز دەست دەکەم بە تەواوکردنی وانەی ڕابردوو لە دۆزینەوەی enthalpy of reaction. Last lecture we have talked about determination of enthalpy of reaction based on the enthalpy of formation for the reaction participant and reaction components. For today we are going to apply to follow the second technique, which is Hess's law. What is Hess's law? Hopefully you remember last lecture when we've talked about determination of enthalpy of reaction, but what we have to do at the first step, okay, if you remember, we have looked at the question at given, okay, if we see delta HF for a reaction participant or any reaction component constituent, that means we have to follow determination of enthalpy according to the delta HF. But for today, we have Hess's law. How we can recognize this technique? How we realize that it's time for Hess's law, okay? Actually, it's very simple. Just by reading the question, you can understand that this is Hess's law, okay? In this technique, instead of general equation, we have some primary intermediate reactions. Instead of general equation, we have a primary reactions, primary equations. Look, Hess's law. The overall enthalpy change in a reaction is equal to the sum of enthalpy change for the individual steps in the process. A very complicated definition. Let me explain. According to Hess's law says that enthalpy of reaction remains constant. And it doesn't matter that the reaction passed through a single step or multi-step. But the point is enthalpy of reaction is constant. How to solve questions according to Hess's law? Remember, how do you recognize Hess's law? Instead of a general equation, we have some primary intermediate equations, reactions, or we have more than one delta HC. Look, if we in any question it gives us some reactions, okay, and you have to manipulate, you have to arrange those reactions according to the general equation, general reaction, in such a way that if we add them together, it ends with general equation with right coefficient. I'm sure that you are not understanding a word still now until I solve a question. So I show you how to solve a question according to Hess's law. Look. Use the following reactions to calculate enthalpy of formation of methane, CH4. Use the following reactions to calculate enthalpy of formation, enthalpy of formation of methane. Look, first of all, in the determination process of enthalpy of reaction, we must have a general equation. We must have a general chemical equation. Look, there is no general chemical equation. In this case, you have to write general equation by yourself. You have to write the reaction by yourself, either according to combustion or formation. Look, enthalpy of formation of methane, enthalpy, okay, of reaction of formation. Look, formation of methane, so that means it's general equation. So first step, you have to prepare general equation based on the unknown. So we have to write the formation reaction for methane. Look, CH4, it contains from carbon plus 2 hydrogens molecule, right? C plus 2H2 to producing CH4. First step, we have to determine delta H for this reaction. Now, what is the given? We can see that Here we have some reactions. If you see some reactions, it means this is his law. This is his law. You have to arrange those reactions. You have to arrange, okay? Some of them maybe we have to reverse or multiply by some number, okay? Reverse or multiply, and in some case we will need two factors for one reaction. It means reverse, then multiply. Okay? Anyway, we have to arrange those reactions in such a way that if we add them together, it must be end with this reaction with the right coefficient. 1 carbon, 2 hydrogens, and 1 methane as a product. Look, I'll repeat to you again. First step, we need a general equation. We don't have general equation, but because of unknown is formation of methane, so we have to write the reaction of formation for this man, which is methane. Then the given, okay, we can see we have some reactions, right? We must arrange those reactions in such a way, okay, that if we add them together, they must end with this equation with the right coefficient. Okay? I have to zoom out the page in order to get enough space to solve this question. So hopefully you see the question clearly. Okay, let's read again. Use the following reactions to calculate the enthalpy of formation of methane. First step, we need general equation. So general equation is formation of methane. Look, methane, because of its formation, we have to write 1 mole of a compound from the product side, CH4. Okay, it contains 1 carbon plus 2 hydrogen molecules. Good. So first step, we have to get delta H. And we have these reactions. Look, I'll show you in a very simple way. Anyone can understand about this. Look, first step, underline each individual general reaction constituent. We have 1, we have 2, we have 3. Okay, if we have 4, no problem, underline them. Okay, 1, 2, 3. Then, search for each individual constituents in the following reactions. Where we have carbon, okay, carbon, only carbon alone, okay, here we have carbon. This is first equation, this is second, this is third. So we have carbon from the first reaction. Then, where we have hydrogen, okay, where's hydrogen? Okay, here we have hydrogen. So hydrogen from the second reaction. Then CH4, it's here. So CH4 present from the third, right? This is not mandatory to have each individual constituents in a series consequence. No, it's possible to have first reaction constituent in the last reaction. It's possible, okay? It's normal. You have to search for them. Then, when you found each individual general reaction constituent in the given reactions, then you have to arrange all the reactions, all of those reactions according to this. Let's start by carbon. Carbon here from the first. Okay? You have to investigate 2 things. Position, number of mole. Position, number of mole. Look, carbon is from reactant side. Here, carbon is from reactant side. Position, it's okay. Carbon from reactant. Position, it's okay. Then, number of mole. We have 1 mole. Okay, we have 1 mole also. So first reaction is okay according to carbon. Don't touch. So first reaction, write as it is. Okay? First equation same. Don't change anything. Okay? Or you can say write as it is, no problem. Okay. Same. Don't change anything in the first reaction. Then, hydrogen, it presents from the second reaction. You have to investigate two things. Position, number of moles. Okay. Position hydrogen is from reactant side here, but here it's from reactant also. Okay, position is okay. Doesn't need to flip or reversing. Then number of mole. We have 2 moles, but here we have 1 mole. So we must change all of them according to this. So multiply by 2 in order to get coefficient of hydrogen 2. So multiply by 2 times 2. First reaction, same. Second reaction, times 2. Then third, CH4. Okay, CH4 is from third reaction. You have to investigate two things. The first one, position, is from product. But here, we have it from reactant. So we must transfer to here. But it's not possible to bring CH4 alone from here to here. Okay? Except of reversing the reaction. So you have to reverse, you have to flip. So the second one, reverse. And number of mole, it's okay, one by one. Reverse. So then, make these changes. Let's make these changes. First reaction, same. Carbon plus O2 to producing CO2. And its delta H must be written in the same value because of we have not touched anything from its reaction, so it must remain constant as it is. Delta H. Look, another thing. Here we have delta HC. Here we have delta H. Here we have delta HC. Doesn't matter because of combustion for 1 mole. Delta H HC equals to delta H. And formation of 1 mole, delta HF equals to delta H. So suppose that each of them is delta H. Look, delta H, combustion of 1 mole, delta H equals to delta H. Delta HC equals to delta H, okay? So delta H equal to negative 393.5 kilojoules. Second reaction times 2. You have to multiply all of them by 2. 2 hydrogens plus half times 2, it's 1 O2. It's producing 2 H2O molecules. Then even value of delta H must be multiplied by 2. So delta H equals to negative 286 times 2. Then reverse the last one, transfer all of them to here and all of them to here. Look, CO2 plus 2H2O to producing CH4 plus 2O2. Very easy. Look, because of we have reversed the reaction, so the arithmetic sign of delta H must be reversed. From positive to negative, from negative to positive. So delta H will be positive 890 kilojoules. Okay. Then let's add them together. They must yield this reaction. Look, O2, it needs some explanation, some clarification. Okay, I'll show you. Reactant with reactant, they are adding together. Product with product, they must be added together. But reactant with product, they cancel each other. So 1 O2 plus 1 O2 will be 2 O2. Will be 2 O2, right? Okay, and with these two O2, they will cancel each other. Then, H2O. Here we have two H2O. It will be cancelled with two H2O also. CO2 with CO2 also. So now, what left? Carbon, 2H2, CH4. Carbon plus 2H2 to producing CH4. About delta H, just you use your calculator and make summation between these numbers, you're gonna get the answer. It's very easy, okay? So the answer is negative 75.5. Negative 75.5. This is formation 1 mole of methanol. 1 mole. This is for 1 mole. For 1 mole. And for 2 moles, we have to multiply by 2. Okay, look. So for 2 moles, delta H equals to negative 75.5 times 2 equals to negative 141 kilojoules. Very easy, just like this. Arrange all the reactions according to the general reaction, which unfortunately doesn't given, but we have written general equation or reaction according to the unknown. Then we have arranged all the intermediate reactions according to this, each individual constituents, okay? Well, let's solve another one. We have this. Calculate enthalpy of formation of 150 grams of pentane, C5H12, okay, using the following thermochemical data or reactions equations. Okay, look, we don't have general equation. Again, we have to write by ourselves. It's formation of pentane. So, formation of pentane, write 1 mole of pentane from the product side. Look, C5H12. It produces from 5 carbons, from the reaction between 5 carbons with 6 hydrogen molecules. So first step, we have to get value of delta H for this man. Then, okay, look, it's for 150 grams, but look, first step, you have to calculate for 1 mole. Then, for how many moles? Multiply by this number. But look, this is gram. Okay, it's very simple. If we have gram, first step, convert gram into mole, right? Convert gram into mole. Mole equals to mass over molar mass equals to mass, it's 150 divided by 72, right? Equals to 2.083 moles. So first step, we have to calculate for 1 mole. Okay, I have to write in a better way. For 1 mole, then multiply the result by 2.083 moles. So first step, there is no option except of calculation for 1 mole, then make interpolation between the result and the number of moles that asked by a question. Okay. As I told you, first step, underline all the components. 1, 2, 3. Okay. Search for each of them. Carbon, it's from first equation. So it's from first reaction, right? Then hydrogen is from second, here. Okay? Second reaction. And then Pentane is from last one, third reaction. Then arrange each of them according to the general equation. Here we have, okay, for each of them investigate their positions and number of mole. Here we have carbon from reactant, it's from reactant, but carbon, it has 5 moles, but here 1 mole, so multiply by 5 times 5. Okay? So the first equation must be multiplied by 5. Then hydrogen, it's 6, it's 1. Position is okay, but number of mole is not, so multiply by 6 times 6. And then pentane, 1 mole, but it's from products from reactants, so reverse. Good. And now let's make the changes according to the general equation. First one, multiply by 5. So it will be 5 carbons plus 5 O2 producing 5 CO2. It's first one. And its delta H must be multiplied by 5 also. Negative 393.5 times 5. Okay? Kilojoule. The second one must be multiplied by 6. So it will be, well, I have to use another color. Look, 6 hydrogens. Okay, 6 hydrogen because we have multiplied by 6. And half of times 6, it will be 3. 3 O2 to producing 6 H2O molecules. And delta H must be multiplied by 6 also. Negative 285 times 8.8, sorry, times 6 kilojoule. The last one must be reverse. The last one must be reverse. Let me show you. If you reverse, what will happen? Okay, bring them for the reactant and bring them for the product. It will be 5 CO2 plus 6 H2O to producing C5H12 plus 8 O2. But about enthalpy, because of we have reversed the equation, so it must be changed from positive to negative and from negative to positive. So delta H will be positive 305.6 kilojoule. Okay, let's check our solution that it's correct or it's incorrect. If we add them together, we must obtain general equation. Let's see. 5 plus 3, it will be 8 O2, and cancel with these oxygen molecules, okay? About carbon dioxide, it will be cancelled with this, so forget about carbon dioxide molecules also. H2O, okay, there will be 0 left amount for H2O, and now what left? 5 carbon plus 6 hydrogen molecules to producing pentane. 5 carbons plus 6 hydrogen molecules to producing C5H12. And for these, as I told you, just use your calculator, add them together, you're gonna get the answer very easily. It's negative 146.7 delta H equals to negative 146.7 kilojoule. This is for 1 mole, okay? But remember, what about 150 grams? So we have converted to number of mole, then multiply your result by 2.083. So for 2.083 moles, delta H equals to this number, negative 146.7 times 2.083, and you can find out the result very easily, okay? So by this way you can follow my steps and you can solve any question. Very good. Another question, I think we will need to solve one more and then we can end the lecture. Look, this one, it's very good and it's very nice. We have seen this we have seen this question many times from the final examination. It's very important, so please understand about this question very deeply and keep them in your brain that it's possible for you to face this question again in the final examination. Okay, let's see. Calculate delta H for the conversion of graphite to diamond, okay, from the following reactions. Look, it's quite challenging question because there is no combustion and there is no formation. Calculate delta H for the conversion of graphite to diamond for the following reactions. We have two reactions, okay? They're related to the conversion of graphite to diamond. How we can use them, but look, without general equation, it's not possible to solve anything by Hess's law. So where we have to take out the general equation, look, there's no combustion and there's no formation, but conversion of graphite to diamond. You must know that graphite is carbon, diamond is carbon also. So conversion of graphite to diamond, it's very easy. This is a general equation. It's general equation. Graphite to diamond. Let me show you again. Look. Conversion of graphite to diamond. Look, this is general equation. Both are carbon. So the general equation will be carbon in graphite form. Okay, carbon in graphite form to carbon in diamond. Delta H. Okay? Using these equations, it's very easy. Let's see. Look, carbon graphite and carbon diamond. We have carbon in a graphite form from the first reaction. And we have diamond from the second reaction. Okay? Second reaction. Very easy. Now, let's check their position and number of mole. Graphite 1 mole, 1 mole. Reactant, it's okay. So same. Same, okay? Diamond 1 mole by 1 mole, but look, it's from product, it's from reactant, so reverse or flip. Okay, let's make the change. Carbon graphite, okay, or I will abbreviate by just capital G, uppercase G, to look, carbon graphite plus O2 to producing CO2, and delta H is negative 394 kilojoules, right? And about the second one, reverse, CO2, okay, to producing carbon diamond plus O2. So the value of enthalpy must be reversed by arithmetic sign. Delta H equals to positive 396 kilojoules. Very easy. Now let's add them together. Look, don't cancel carbon of graphite with diamond. They must remain like this. So O2 with O2, CO2 with CO2. Okay, so what will left? Look, let me show you. Carbon graphite producing carbon diamond, and delta H will be, come on, okay, delta H will be, look, negative 394 plus positive 396, it will be positive 2 kilojoules. So because of its endothermic, thermodynamically, graphite is more stable than the reactant, thermodynamically, because of its endothermic. The energy of diamond is greater than energy for the graphite. Okay? ئەوە کۆتا پرسیار بوو لەو بابەتەی قوتابیانی ئازیز هەرچەند پرسیارێکی حەلکەم هەمان فکرەیە هەر ئەوەندەیە تەنها ئەوەیەکەوە هاوکێشەی گشتی نادا کە دەبی بە خۆت بینووسی پاشانیش ئەو ڕیئەکشنانەی کە دەیداتن ڕێکی دەخێن بە گوێرەی هاوکێشەی گشتی و ئەنجامان بەدەست دەکەوی. بەم شێوەیە کۆتایی بەوانەی ئەو ڕۆمان دێنین هیوادارم سوودتان لێ وەرگرت بێ تاوانێ داهاتوو بە خواتان دەست پێرم هەر شاد و سەرفراز بن خواتان
گروپی لاس